I'm going to start with a timeline of knowledge elicitation. So to illustrate how this brainstorming session, our brainstorming session at least, have evolved since 2010. So we have created Bayesia in 2001. So I guess lots of people here know that. In 2002, we have released the first commercial release of BayesiaLab, so BayesiaLab 1. And in a few weeks, we're going to release BayesiaLab 11. And we had our very first brainstorming project in 2007. It was indeed in the context of an MBA project with a friend of mine, and it was for a French bank in order to try to capture what were the drivers of the performance of agencies for this bank, right? And so it was really a very interesting project. During a week, we spent a week with these experts, and we have been able to create a Bayesian networks that answered, and that we have been able to use for identifying what were the most important drivers for the performance of these agencies. And then it was like, opening a door. And so during the next 3 years, we have carried out like 5 or 6 brainstorming, other brainstorming projects with other customers. And they were successful because at the end of the day, we were implementing what is described in Noise, the books that have been released last year, and where, perhaps those who were at the conference last year remember the talk from Olivier Sibony, where they are describing in this book what they call the decision hygiene. So at the end of the day, we are implementing decision hygiene since 2007, where the two main topic in this are, using a group of experts and splitting the question into sub-questions, right? So this is exactly what we do with Bayesian networks. And so we have done these 5 or 6, and obviously, as you may know, we have a strategic partnership with P&G, and so obviously we have done one project with them, and it has generated lots of interest in 2008 or 9, and then they say, okay, so it looks very promising, but still we are not sure about the quality of the model. So they sent us 2 observers from the US for a brainstorming session we did in Brussels. And these 2 guys were just observing the session in order to judge the quality of the session. And the result was that it was good, but full of biases, right? And so they gave me a kind of ultimatum saying, well, you have to find a solution to reduce these biases. And then so we have studied a lot in order to find what can be done. And so I've studied a lot this book, Thinking Fast and Slow, and then have been able to identify these cognitive biases. And we have designed BEKEE. So BEKEE stands for Bayesian Elicitation Knowledge Environment, and Elicitation Environment, sorry. And indeed, what we do here, it's a web platform that is connected to BayesiaLab, and that allows us to implement a Delphi approach, at least for the quantitative part, when we are eliciting the probabilities. Right? So it was a solution indeed, and so it was satisfactory for P&G. And then during between 2010 and 2020, we have used BEKEE and BayesiaLab for a dozen of other projects, right? So not very strong activity, but still very interesting and very, very different topics. And then in 2020, we started to work with L'Oréal in this topic. And I think it's mainly because of the Book of Why. So they read the book and say, okay, we need to create causal Bayesian network in order to help our business units. And so they did a presentation in the Bayesian conference in 2020 in the Laval Virtual World. Then in 2020, well, last year, at the end of the day, we have introduced, the BayesiaLab ICI, so in independence of causal influence. So this is something we had to use in order to ease the brainstorming session, because because of the pyramid, building Bayesian network by hand is quite time consuming. And if you want to use 3, 4, 5 parents for a node, you have an explanatory, a combination number of probabilities to elicit that is increasing exponentially. So it's like 1 minute per distribution. So it's very, very quickly time consuming. And then so the idea was to use this independence of causal inference in order to increase the number of parents and reducing the time to elicit these probabilities. So this is something I described extensively last year in the conference. So you can still have access to the videos that have been recorded. And we had also a presentation from Jan from Charrier, so who described, one of our projects, a project we did last year for him for, predictive maintenance, right? And so in 2022, so first between 2020 and 2022, we have carried out more than 25 projects. So you can see that there is a very strong increase in the number of projects. And so I guess it's because mainly of this ICI feature. And also now we have added a new feature. Well, it's not really a feature, but it's a new approach. So we are now able to use also a Delphi approach in the qualitative part when we are, eliciting the dimension of the domain, right? And so this year, tomorrow, in this conference, you're going to have a presentation from Jan again that will describe what has been done with the network we have created last year. And also a very nice presentation from Hussein from L'Oréal tomorrow afternoon, in France, where he's going to describe what we have done 2 or 3 weeks ago. And it was a very fascinating project because we did a brainstorming session with L'Oréal in order to know when to use BayesiaLab for brainstorming sessions. So this is really a meta approach here. So for the very first time, I was not only a BBN modeler, but I was also an expert. And I think it was very, very successful. I was really impressed with because usually, I was like in the shoes of my customers. Usually they say, well, it works for the other one, but it's not going to work for us, or it's going to be more difficult. And I was exactly in the same spirit saying, well, I'm not sure it's going to be applicable for this. And I was wrong, obviously. And this was very, very impressive. So we came up with a very, very nice model that Hussein will show us tomorrow. So let's now talk about really the topic of priority or knowledge elicitation. So the context is we use this approach when there is no data or not enough data for using our very nice library of machine learning algorithm. And one of the interesting topic is that the experts that participate to the session are usually, they don't know anything about BBN. So they are expert in their field, but they are absolutely not expert in the Bayesian network field. So it's a challenge here. The objective of this session is usually to answer a strategic question, right? It can also be for, capitalizing knowledge. So we had a few sessions last year for trying to capture knowledge of people who were about to retire a few weeks or months after the sessions. It's also very good for team building, for training, because at the end of the day, you have a network that represent the domain and that can be used for describing the domain to people that are new in this field. And the output of these sessions are, so at the end of the day, we have two kinds of scenarios. The first one is we have a model that we can use for analyzing the domain, for answering the question. And once it's done, once we have the answers, so at the end of the day, the network is not used anymore, right? Or the second scenario is to really use this model as a ProASIC expert system. And then what we do is we publish it as a web simulator. We can also use APIs. So now we are using REST APIs for building web application or building, apps. And so then this allows our customer to plug the model to their information system. There are some particularities for this project. Is that the thing is usually since it's a strategic question, the topics are usually confidential. So which means that there is no way to share what we do with other customers. So when customers are asking, oh, how does it work and so on, so we have to use slides with virtual example and so on, or fictitious example, but it's sometimes not really convincing. So it's quite hard for them to really imagine what their brainstorming session will look like. So, and it's still true, except that, so when I was preparing this presentation last week, I said, well, perhaps I can find a fictitious example that makes some sense. And so I find one, well, you're going to say perhaps it does not make any sense, but anyway, it allowed me to go through all the steps of a brainstorming session without any confidentiality problem. And here, so the topic is, what are the drivers that have an impact on the sensation of cold, right? And for that, so I have recorded 6 videos. So the first one is about the elicitation of the dimension of the problem. Then the second one, the creation of the structure. Then we're going to go through the elicitation of the probabilities, how to analyze the probabilities that have been given by the experts, then use data for parameter updating, and the last step, the publication of a web simulator. So it's like, I think, 30 minutes of videos, so I should be on time. And so let's start with the first one. So the elicitation of the dimension. So I'm going to go through here 5 main topics. So the creation of the experts, then how we elicit the new dimension with the new methodology. Then we are going to use BEKEE, see how we generate nodes from the comment field that have been used now for finding or for allowing the experts to populate or to give their opinion about the dimensions. And then we are going to create the nodes that correspond to the dimensions, right? So it's working. So here, so we start by obviously creating a network. Then first option is to create the expert manually. So here I'm adding myself. And so we have here, because we did create avatars, use a comment field for describing the field of work. And something that is new is we can have now a color associated with the experts, right? And so these colors, they are not mandatory, but they allow to identify very quickly the expert. So the second option is to use, instead of creating the expert manually, is to use BEKEE and to import the expert via BEKEE. So here, we have these experts, which is not only an expert, but also a manager, John Doe 0. And so he's a manager of this account. And we have here 5 experts that have already been associated with this session, right? So if I open the session via BayesiaLab, I'm going to be able to automatically collect these experts. So there is something new here, is a send out invitation, because before, when you create a session like that, BayesiaLab automatically send emails. So here now, this is an option, right? So we create this. We have collected the experts with their avatars. So when the session is open, there is no way to edit the experts. So I have to close the session, and then we can associate the colors with the experts, right? So again, it's not mandatory, but it can help to identify the group of experts sometimes. And now this is where I'm going to describe our new way to elicit the dimension, because before it was like we were talking with the group and finding or asking what are the drivers, the main drivers for you that are important to incorporate in the model. So now what we do is we create a node. And so here the name of this node is what are the top 3 dimensions for feeling cold. And so indeed, it's not really a probabilistic node. So we have 2 states here, false and true, but this is not something we are going to use. We are going to use the comment field here. And we are just here defining, so using this command field for describing the question we're going to ask to the experts, right? So what are the top three dimensions for you that can have a causal impact on feeling cold? So then we open the session, right? And then we are going to post this question to the experts. So I have to open the node, go back to the probabilities, even though, again, we're using that for probability elicitation, but this is a way for us to send the question, right? And then, so the expert click on the go button here, and he has a question. So what are the three top dimensions? So again, we don't care about these probabilities here for this one. Oops, sorry. And here in the command field, so the experts have to enter their top three dimensions. So they can obviously define more than three, but here the question is three. So they define a list here. And then, so, oops, sorry, it seems I have a problem here. Let me go back. Okay, sorry about that. All right. So the first expert is giving the main three dimensions. And now, so thanks to the features in BayesiaLab, we can, follow what are the experts that answered. So we have the list. And here, each of these experts is giving the probabilities. So we have the progress here, everybody answered. Now we collect all the dimensions, right? And so this is a new feature here. I can automatically generate nodes from these comments, right? So as you can see, now we have these sticky nodes, one color per expert. And now the thing is, we now have to analyze all these sticky notes. So this is pictures that I took last month. So we had a session with the customers, and as you can see, we had 28 experts. So which means that this guy here, the facilitator, has to really understand the domain, because then you have to analyze, each item and see if they are synonym or not, and really know if they mean the same thing or not. So this is not something that is easy to do. So this is the reason why you need a facilitator that understands the domain. And then, so here in my example, it's much more similar, right? So I have this. So now I'm creating the node. So I'm using the first expert. And once it's done, I'm closing the sticky note. So we have some redundancy here. So everybody talk about temperature, for example. And for example, the John 4, everything has already been mentioned, so there is nothing to do for him, right? So this is very, very interesting, because it's not only, it's not only efficient for collecting the knowledge, but it's also, it allows to reduce the biases, because before, when we were asking what are the main dimensions, we had the first one we were talking, well, we had a very strong anchoring bias, right? Because then after that, everybody is reacting, adding some dimension on top of this one, but then it's too late. You have this very strong anchoring bias. And you also have some experts that are just not really motivated, and they're just listening. And at the very end of the day, they say, well, okay, well, everything has been said. I don't have anything to add. So now with that, everybody is participating. So you have to give your three drivers in that example. And so it's not only very efficient for reducing the biases, but it's also very efficient for collecting a broad view of the domain, since you don't have these biases. And I was quite surprised that the very first time I use it, I think we saved 2 or 3 hours in the session, thanks to this, because very quickly we can collect all the dimensions that matters, right? So now I'm going to switch to the second video, where we are going to talk about the creation of the structure, right? So we're going to create concepts via the classes, define the states, and then choose if we are going to define interaction or use our new ESIEA features. So now we have our nodes, and we delete the node. We're going to delete this node later. And then, so we start by grouping the nodes. So temperature, humidity, and wind, we can assume that they belong to one concept. Radiation, clothing belong to another one, and these four belong to the last one, right? So we have something like the weather concept, then we have the external condition, and we have the internal condition. Right, so I'm creating classes in order to capture this concept, right? So 3 classes here, and as usual, I'm going to define associate color with these classes to quickly identify the nodes. Right. So now we create the target node. Right. So this is called filling code. 2 states, it's true or false. I set it as a monitor and then as a target node. And then for temperature, we have to define what are the states. So here I chose 3 states from -10 to 16, 16 to 20, and 20 to 40. And then for the other one, so it's going to be super fast because again, we don't really care about this example per se. This is really the methodology that matters here. So we have the different states for each node. Right. And then, so here, this is something I strongly recommend, is to use the feature we introduced last year, increment and save, which allow to, you see here, you have a filling code 2. So this allows you to have some kind of versioning, right? Here, this is also something new. So we have this stretch and shrink, horizontal and vertical. So very useful for formatting your network. And now we have to decide, so to create the latent variable to reduce the complexity, because obviously we are not going to connect these 9 nodes together. So here we have defined that temperature, humidity, again, bear with me 1 second. It's not so easy to use videos because, all right, here we are. So yes, so we have decided to use these 3 nodes, so within the same concept. So, and now we assume that temperature, humidity, and wind have interactions, right? So we then add directly these 3 nodes as parent. And what I had here was the states. So we have used 3 states, -1, 0, and 1. So -1 to indicate that this is strongly decreasing the feeling of cold. 0, it's neutral, and 1, it's increasing the feeling. And then, so we are gonna do the same thing for radiation and clothing. So we create the latent variable external condition. Then we are gonna assume now that there is no interaction, but instead we are gonna use the ESIEA approach. So we select these 3 nodes, we go to ESIEA, and then we select the output. And then we have to choose a combination function, right? So remember from last year, so you have the long list of available combination function. Here I'm choosing an OR, for example. So by selecting a mechanistic local effect, I can create a noisy OR without using equation, right? And then, so if I do that, I'm going to have automatically my noisy OR implemented. We have these new features, the undo, that allows to cancel what you have done. And so here, because this is not an OR that I want to use, so we have added some new function here. So you have sum plus, so it's for defining just positive effects. So here, automatically we have 0, 1 to say this is either neutral or it will increase the feeling of cold. And then, so here, this is not what I want either. So I'm going to go back to ESIEA. Then here we are. I can here use now the sum minus. So here you see I did something wrong because I forgot to select the output, right? And so when you use sum minus, you are defining only a negative effect, which here will decrease the filling of column. And so what we want to use in this one is the sum zero. So this is a symmetrical one. So this is here a new feature that allows to define prefix for the effect nodes. So very useful when you have lots of different dimensions, right? And so here I'm using EC. So this will create nodes with an EC prefix, right? So EC effect 1, EC effect 2. So it goes from -1 to 1. Then I have this node that goes from -2 to 2. And at the end of the day, I don't want to use my external condition effect force through, but instead I'm going to use this -2 plus 2 to be able to really capture very strong effect, positive and negative. Right? So after that, same thing for the internal conditions, right? So we create the latent variable, internal conditions. We are going to define only 3 states, -1, 0, 1, just to be able to have positive and negative effect, but not that strong. And we use an ICI model here. Sum 0, the symmetrical one. We change the prefix. And then we have this new network, right? And after that, we have to check the mapping function. So the function that allows to transform something that is numerical to something that is force through, or at least the output of the ICI model, right? So here, by default, we have a kind of sigmoid. And this is not exactly what I'm looking for here. So I'm just going to use, a bounded identity function. So when it's less than -1, it's -1. When it's more than 1, it's 1. Okay, so I'm saving this network, and then we are going to do the same thing for the target, right? So we have to connect the target with these 3 latent variables. So I'm selecting these 3 nodes, then go to ICI, and we are also going to assume that this is an independence of causal effect, right? Symmetrical. We don't need any mechanistic local effect here. We change the prefix, and we create our substructure. All right, which is the sum here of these 3 different effects. Same thing, we have this sigmoid that we are going to change here with just when it's less than 0, it's false. When it's more than 0, it's true. And one of the last steps is to remove the formulas because we have overwritten them. So we just delete the formulas. And we're also going to change the image that have been associated automatically with the nodes. So we're going to use an image corresponding to the thresholds here. Right? We save the network. And now here we see we have 12 distribution to elicit because we have chosen to use an interaction between these 3 nodes. This one, we have only 2 distributions, and at the end of the day, only 1 because we have a neutral state. So here, when there is no radiation, we are not going to have any effect here. So it's going to be 100% on 0. Right? So this is something we try to use a lot, this neutral effect. You can also see that we have added this new feature. So we are automatically generating a causal question, right, in the comments. So here, what is the independent local causal effect of radiation on external condition effect? So this way, the expert will really know what we are expecting from them. And for this one, we go through same thing. neutral states. We have the question automatically generated. All right, so here we have defined our structure, right? So we have the qualitative part, and as you can see, we have these warnings with most of the nodes because we still have to populate the tables, right? So this is now what we are gonna go through with this third video. So this is the quantification of the network, right? So again, this is a fictitious example. So I've used 5 different experts, but I was the only one behind them. So what I did is I manually created the priority for one, and then changed slightly for the other one. And I use BEKEE, but in batch. So this is here the illustration of using a batch session, even though in real life, we are not using the batch session for this step. We use it for, for not what we call validation, but more verification of the model, for allowing the expert to go through the priorities they have given, or to allow people that were not present during the session because they had some problem. And so this allow them to populate the table they have not been able to do during the session. But here, so this is something I'm using. And so I'm opening the batch session. I'm just going to send 7 questions. So those corresponding to the effects. And this is a new feature too, where we can check these boxes in order to send the prior. So this will allow me to directly send the neutral states, right? So the priority I've already populated. And we have the same option here, send out invitation or not. So we open the batch session, then we switch to BEKEE. Our experts will run this batch session, and we have these 7 questions, right? So we just have to click on run, and then answer the question. So here the context is radiation is false. As you can see, it's already populated with 100% on 0. So we have now set the confidence by default equal to 50. So this is more interesting than starting 100, because now people, it's again kind of anchoring biases, but they can at least decrease or increase their confidence based on the question. Then, so we have here in the context of radiation equal true. So this expert is just saying, well, 75% of -1, 25 of plus of 0. So you can see that now we have the automatic checking of or locking of the priority when we edit the priority. And then here, so this is defining a negative effect on external condition, right? So reducing the priority of filling corp. We have this new option. We can uncheck show sliders. So this is something we added because when experts are using sliders, we usually collect probabilities with, like this one with lots of decimal points. And so I think it's better to allow the expert to directly enter the priority manually. Now let's assume that we have all the probabilities. So every expert answers the questions. We close the batch session in order to collect the distributions. And here, so we have the priorities that have been given. So you can see you have some cells that are highlighted. So when it's highlighted, this means that we have some disagreement among the experts. So we are not looking for a consensus. We don't want all the experts to be to agree, because otherwise we just need one expert. But when we have divergence, usually, or at least when there are some mistakes, we have a divergence usually. So it can indicate that there are some mistakes. So here, when we open the table and have access to the probabilities, we see that we have a very strong divergence between John 1 and John 2. Right, one said 90 for -1, the other one 10. Right, so this is the reason why. It's highlighted. right? Then we're gonna again save this network to a version 5, and we are gonna do some formatting in order to, to clean a little bit this network, because we have lots of intermediate nodes here that they do not bring information, at least qualitative information. So we just gonna remove their name, right? So we select these nodes and we uncheck show name. So this allows to have something similar. And these root nodes have not been elicited. So we are just gonna define a uniform distribution for these drivers. So now we have a fully specified Bayesian network. Right? So all probabilities have been set, and I'm just here copying the format of internal condition effect in order to have monitors associated with all the drivers. So just to indicate that these nodes are input nodes, if you will, right? So we have now our networks that have been fully specified. So this fourth video is for illustrating what we do once we have these probabilities. So the idea is to analyze the assessment, to see if there are no mistakes or anything like that. And we are going to see a new feature that allows to measure the Hellinger distance between the probability given by the expert and the consensus. And I'm going to conclude with expert network learning, which means using machine learning for finding the relationship between these experts. So here I'm going to use analysis, visual, and sensitivity expert assessment just for, I don't know if you are ever use this feature. This is for generating, in this example, 50,000 networks where each probability is going to be sampled among the probability given by the experts, right? So you have 3 options, but here I use the last one, so which means that it's really a huge mix of distributions, right? And so you have to define what are the parameters and what is the target. So here by default, it's already done. The output is set as the target node is set as a target, so which is the output. And we are sampling in the probability given by the expert. And we have this distribution for false and true. So in red, you have the distribution of false, right? And in gray, the distribution of true. So as you can see in the monitor of filling call, the probability of false is more or less 70% and true is 30%. So we have this normal distribution, almost normal, but we have a very strange distribution in the middle here, right? So this means that we have some problem, right? So then in order to investigate, I'm gonna check here, add 2 nodes in the analysis. So the 2 intermediate nodes, external and internal conditions. And here, this is external condition. So if I go through the different states, so -2 looks okay, -1, you see there is a huge range. Same thing for +1. So this means that some probability distribution are probably wrong, right? Or at least there is something strange. Here for internal condition, it looks okay, right? So we are gonna here use also mapping 2D just to illustrate new features here. So if I go there, now we have added 5 new metrics. So the number of assessment, the assessment completion rate, maximum divergence, overall divergence, and the missing value rate. So that we can use for defining the size of the nodes or the colors. And here I'm gonna first start with the assessment completion rate. So we can see that all the probability have been given. We have these new options that allows to hide the label of the nodes that we are not analyzing. So this is very useful for cleaning the mapping. And here now I'm choosing the size of the nodes. The metric is the overall assessment divergence. So the bigger the node is, the stronger the divergence is, right? And also the color based on the maximum assessment divergence. So we have also a new feature here because you see we have the color here depends. So the stronger the value is, or the higher the value is, the greener the node is. So which is here, since we are talking about divergence, it would be better the other way around. So we have this new option, very convenient, that allows to reverse the colors. So now it's going to be red, right? And we can see that these two nodes, so closing effect and age effect, have very strong divergence. So which means that perhaps we have some errors here, right? So we are going to go analyze these nodes. So we open the clothing effect, and indeed we have these highlighted cells. And if we go through the assessment, we can see that indeed here, John 2 probably inverted the state. So this is something very, very usual. So here we just fix it manually, right? So this happens, I would say, in 25% of the case. Right? And so here, once we do that, there is no yellow cells anymore. And for age here, if we analyze these dissolutions, we still have these yellow ones. And we can see that John 4 did not answer, or at least gave uniform dissolution. So it probably means that it just clicked on validate without doing anything. So we just set a confidence of 0 because we don't know exactly what he meant. Or if he is in the room, obviously we can ask him to fix this probability, but here is not, right? And now we are gonna remove the assessment. So this is something new, a new feature that allows to delete all the zero confidence assessment. So a zero confidence assessment does not change anything about the consensus, but here just for cleaning the database. Right? So now we can see that they don't have the exact same number of assessments. And we are going to check. So Control save before and check if we still have errors. So we use a sensitivity tool and generate the analysis. And we can see now that we have these nice normal dissolutions here. And very quickly, usually what we do is also kind of quick analysis of the strengths of the driver. So the most efficient way to make a right click on the monitor panel and use a sort function that allows to sort the monitors in order to see what is the most important one. So here we see that this is a weather effect, the most important one, then internal condition effects. But these are not drivers, so they are latent variables. So we are going to set them as unobservable. So I'm selecting all the root nodes and I'm inverting the selection and set all these nodes as not observable. Right, so now they're going to be excluded from all analysis. And I'm going to generate a tornado diagram based on total effect just to see, right, the effect of all these drivers. Right, so we see that temperature is obviously the most important one. And we go back to our assessment, and we're going to now analyze the consensus. So here, to do that, I'm creating another expert that I'm calling consensus.c.com because we need to have an email. So it's obviously not a correct one, but we don't care. And so I'm associating a green color with this consensus. And now I'm selecting the node with assessments and make a right click on them to generate assessments. So here, this is a new function that allows me to generate, assessment by using the table, the current table. I'm assuming that this is the priorities that have been given by the expert I've selected. So here I've created an expert called consensus, and this guy has 28 questions or answers. And these are the consensus of the group, right? Now I have this assessment report that I can generate where, we have so all the information about the time and so on is not that important. But now we have this color coding report where we added the confidence in a column. So it's color coded from red to green. And we have also color coding for the distribution. So the darker blue it is, the more disagreement we have in the probabilities. Right? So as you can see, it's a huge report because we have for each probability distribution, conditional or marginal, we have, in this example, 5 or 6 probability distribution corresponding to the experts. So in this one, I just selected, I select the option to generate a report with only the expertise where we have comments. So we had only the consensus. And this last option is to focus only on the table where we have a strong disagreement. So here I've selected 30%. Right? So this allows to clean the report and focus only on the most important things. And now I'm going to introduce a new report that we have here. This is the Hellinger distance analysis report. And so for those who are not familiar with this distance, I'm going to show you the formula. So I'm selecting a consensus as my reference expert, right? And we are using this formula. So I'm not going to spend time on this, but for your information, this is this Hellinger distance, very interesting one. And then, so you have these tables that measure the distance of all experts with respect to my consensus here. So we see that this is John 0 that has the smallest distance or shortest distance with respect to the consensus, and 12 assessments that are the closest one to the consensus, right? And you have that for all nodes. And so the last step of this analysis will consist in using machine learning here. So what I'm going to do is export or create a data set with the assessment, right? So I just go to Tools, Assessment, and export expert assessments. This allows me to create a CSV file where I have one row per probability distribution, right? And as many columns as expert plus twice because we have also the confidence, right? So we have here, you see probability plus confidence for each probability that have been elicited. So I'm loading this data. Everything is turquoise because everything is continuous. I'm removing the missing values just to focus on the probability that have been elicited. Here, this is a new discretization algorithm. So this is called binary mean. So this is a very simple one, but that allows to define a threshold equal to the mean value that takes into account weights if you have, right? So this is what we had before by default. When you switch to manual, you had a threshold that was set to the mean value, unweighted in this case. So now we have the possibility to generate threshold automatically that correspond to the weighted mean, right? So we do next here, and I'm gonna generate here the discretization by using the R-squared genopt for the probability of the consensus, right? And export this discretization to all nodes, right? So which means they are all using the same threshold. And I'm gonna delete the nodes that represent the confidence. Right? So we delete the nodes. And we use machine learning to see that we have indeed a consensus that is in the center of this network, right? So so everything is based on correlation, obviously here. So I'm associating images, changing that into badges, and then we use monitors just to highlight that we have probability distributions. And then when we switch to validation mode, we can play with that. So you see the impact of observing value a priority for consensus. We see directly the impact on the other nodes. So I've done the same thing since it's already 3 and 5 minutes. I think I'm gonna accelerate and just go through this one, parameter updating, because this is quite important. So here this is when we have, data that is available, and we want to use it in order to improve our model, right? So here I'm assuming that I have almost 180 particles that have been described in this data set, and I'm going to use them for, creating new experts. So here I just go to experts. I have created 3 additional experts, so P0, P100, and there is another one below. And now what I'm going to do is save this uniform distribution of the root nodes in the consensus to be able to go back to this distribution in a few minutes. And use now the data for creating my first new expert. So I switch to validation and then select my nodes and use parameter updating, where I'm defining that I'm not going to use any directly priors, right? So it's really like now using the batch processing, I'm using the maximum likelihood estimation and for the nodes that are directly observed, and expectation maximization for the hidden nodes, right? So after convergence, now I have a new table, and I'm going to directly save them. So I open the data set, the tables, and I can see that the very last one, there is a uniform distribution, which means that there is no data for this scenario. And here I will use this new feature again. So I'm creating or associating these parameters to my new experts, right? And I go back and I can use this feature, generate from assessment, that allows me to go back to the distribution that corresponds to the consensus. Right? So now we are back to the consensus. If I go here, I can see that in red, I have the distribution corresponding to my first parameter updating. Then I use another one. So where I'm going to assume that now I have directly prior. So I'm assuming that my experts correspond to 100 particles. So I'm going to use these 100 particles and this network and merge them with the 179 that are described in this data set. So now it's like maximum a posteriori instead of maximum likelihood estimation, and I have expectation maximization with directly prior. I'm saving these parameters in the second expert. Go back here to the table to have a look at the priority distribution. And we see it's not that far from the other one. So it's in between consensus and without directly. And here we don't have observed anything, but since we have a prior, we kept the initial distribution. I go back and restore the consensus in order to illustrate the last one, where here I'm going to simulate the fact that I have data that comes incrementally. So I'm going to use incremental updating, but with directly prior, because without, obviously, it does not work. So here we are simulating that data is coming, perhaps it's every day, every week, we don't know. But we are using every day here the data for updating the probability. So after this 179 observation, if we have a look at the priority distribution, we can see in a few seconds that it's also close to the other one. So we have these 3 ways to create new experts, right? So either just purely using the data for creating the new expert, or using prior, directly prior. And the last step, so super quick because I'm late. This is a web simulator. I'm going to be quick because you know how it works. So just here, I'm creating here, associating images and so on, defining the input outputs, right, with gauges here, remove the image. And then we have the preview. And so this is usually what we do at the end of the session. We publish directly the model. So this allows the expert to play and verify the quality of the model. Indeed. Because then they can directly go to their web simulator and play here. So this is an adaptive questionnaire. Each time we set one evidence here, we are updating the output on the right. Right? So this is the result of this session, if you